All right, so the purpose of this video is gonna just be to discuss this correlation coefficient, which is something you probably saw in Introstat, and so it might be a little bit of a review. But remember, this correlation coefficient, which we're gonna denote as R, is gonna measure the linear relationship between two variables. And so in particular, we're going to see what the correlation coefficient is for this example where runs scored is the response, batting average is the predictor. And then in the handout that accompanies this, you're going to compare it to the correlation coefficient with using that newer baseball statistic, the on-base slugging percentage, just to see kind of how much better or if it does better than the batting average does. And so the correlation coefficient is only to be used when the relationship between two variables is linear. And so we already noted in our scatter plot way back on page 3 that this relationship did look linear because there's no curvature. So that means we could use this correlation coefficient. It's always going to be between -1 and 1. And so -1 is going to be a perfect negative linear correlation. +1 is going to be perfect positive linear correlation. And in general, values closer to 0 indicate weaker correlation. All right, so let's just kind of draw some rough sketches of kind of scatter plots with various correlation coefficients just to get kind of a better idea. None of these are going to be exact, of course, but if we were to draw maybe a scatter plot with a correlation coefficient of 0.4, that's going to mean that the relationship is positive. And 0.4 is kind of like a moderate to weak correlation, so the points aren't going to be super clustered around a fitted line. And so maybe something like that would be a correlation coefficient of 0.4. On the other hand, a correlation coefficient of -0.9, that's going to indicate some pretty strong negative correlation. And so now when we draw our example, the points are going to be a lot more clustered around some fitted regression line. And because it's negative, the slope is going downward. Our kind of last little example is going to be a correlation coefficient that's really close to 0. And so that's going to be a really, really weak relationship where you could almost like barely even tell whether it's positive or negative. But because it is slightly positive, the line might be kind of sloping upward a little bit, but the points are really, really scattered, and there's not really much pattern between X and Y. All right, so kind of using the examples that we just drew out, take a second to kind of guess what you think the correlation coefficient would be for this baseball example with runs scored and batting average. All right, so when I guessed, I kind of thought around 0.7, but really anything in that ballpark is good. So it's got to be positive because we see that the relationship is positive because the line's sloping upward, and it's kind of moderate. There's R code kind of given here so that you could use it in the your turn section to figure out the correlation coefficient. But for this particular example, R actually turns out to be 0.81. And so again, this correlation coefficient, it's just a metric that you'll see a lot, or kind of a lot in the literature, depending on the study that you're reading, just as a metric for the strength of the relationship between two variables. And so it's usually just a descriptive metric, and the closer to 1 or the closer to -1, the stronger the relationship. Okay, and so the last part of this section about interpretations, we'll talk about interpreting the fitted intercept as well as the fitted slope before moving on to a discussion about the model error term.